All right, for this lesson, we're now ready to use the Laplace transform to solve an initial value problem. So we're going to start off by solving this problem here. Now, all of these first three problems that I'm going to do today are all problems that we could do using methods that we learned earlier in the course. And it's probably easier to use those methods, but I want to just show you how to use the Laplace transform. And by the time we get to the fourth example, we'll actually be using the Laplace transform to solve a problem that couldn't be solved using our earlier methods. All right, so starting off here, the first thing we're going to want to do is take the Laplace transform of both sides of this equation. So we're going to get the Laplace transform of the second derivative of y minus 2 times the Laplace transform of the first derivative of y plus 5 times the Laplace transform of y is equal to, and now the Laplace transform of this, notice that this is just a constant times e to the at, where a is -1. So this is going to be -8 over s minus -1, so plus 1. All right. Next, notice that we've got these the Laplace transform of a derivative, and we talked about what to do with those. We said that the Laplace transform of the derivative of a function is equal to s times the Laplace transform of the function minus the function at 0. And we said that the Laplace transform of the second derivative is equal to s squared times the Laplace transform of the function minus s times the function at 0 minus the derivative of the function at 0. All right, so now let's plug those in up here. So first, the derivative of the second, or the Laplace transform of the second derivative is going to be all of this. So we get s squared times the Laplace transform of y. And by the way, you don't have to keep writing this Laplace transform of y. You could just set that equal to define that as being equal to y of s, or just y. But I kind of like writing the fancy L's, so I'm just going to leave it like this. So we get this minus s times y at 0, which we're told is 2, so this is going to be 2s, minus y prime at 0, which is 12. All right, that's this part. Now -2 times the Laplace transform of the derivative, so we get -2s times the Laplace transform of y. And then -2 times, this is going to be -2, so it's going to be plus 4 when we distribute that -2. And then plus 5 times the Laplace transform of y is equal to -8 over s plus 1. All right, now let's factor out these Laplace transforms of y and then move everything else over to the other side. So we're going to get the Laplace transform of y is equal to, Laplace transform of y times s squared minus 2s plus 5 is equal to -8 over s plus 1 plus 2s, and then this is going to be -8, so this will be plus 8. All right, we're almost done. We just need to then get a common denominator here, combine this, and then divide it by all of this. So let's see, this 2s will become 2s squared plus 2s over s plus 1. And then this will be 8s plus 8 over s plus 1. All right, so the Laplace transform of y is equal to, let's see, combining those 8s will go away. It's going to be 2s squared plus 10s over, let's put this on the bottom here, s squared minus 2s plus 5 times s plus 1. So there we found our Laplace transform. Now what we need to do is take the inverse Laplace transform of both sides to get this equal to y and this into the t domain. All right, so let's put this up here. So we have the Laplace transform of y is equal to 2s squared plus 10s over s squared plus or minus 2s plus 5 times s plus 1. And this is actually identical to the last example in the last lesson. But I'm going to go ahead and do this again. So we need to use partial fractions here. So let's set this 2s squared plus 10s over all of this minus 2s plus 5 times s plus 1. Set that equal to, remember, we're going to need to complete the square here. And so we're going to get s minus 1 squared plus 4. And then on top goes a times this, s minus 1, plus this, b times this, the base here, so 2b. And then this is going to be plus our some constant c over our other factor, s plus 1. And then to find these, let's multiply through by our common denominator here. We get 2s squared plus 10s is equal to all of this, a times s minus 1 plus 2b times s plus 1 plus c times s squared minus 2s plus 5. And then let's plug in some values for s that are going to make this simpler. So we start with -1. If we plug in -1 here, we're going to get -8 is equal to, this whole thing will go away. -1 squared is 1, plus 2 is 3, plus 5 is 8, so 8c. So we get that c is equal to -1. And then if we plug in -1 to get rid of this term here, or positive 1, this becomes 12 is equal to, this goes away, this becomes, this 2 times 2b is 4b, plus 1 squared is 1 minus 2, -1 plus 5 is 4c. But we know that c is -1, so this is going to be -4. And so b has got to be equal to 4, right? 16 divided by 4. All right, and then the last step we took was we plugged in 0 for s. So this became 0 is equal to, this becomes 1. So all of this is just -a plus 2b, which is 4, so 8, plus c times, let's see, 0 is going to be 5, so 5c, so this is -5. And so a is going to be equal to 3. And then we can go back up here and replace this. So we get, plug in a 3 for that A, and a 4 for that B, and then a -1 for the C. All right. Now we're ready to take the Laplace transform of this. So if we take the inverse Laplace transform of this side, we get y. And on this side, we get the inverse Laplace transform of, or actually 3 times, let's pull out that 3. 3 times the inverse Laplace transform of s minus 1 over s minus 1 squared plus 4, which we wrote as 2 squared, plus, let's see, 4 times the inverse Laplace transform of 2 over s minus 1 squared plus 2 squared, minus the inverse Laplace transform of 1 over s plus 1. Okay, and now the inverse Laplace transform of this is e to the at cosine of bt, where a is 1 and b is 2. So this is going to be, so y is going to be equal to 3 times e to the t cosine of 2t. And then this is the same thing. This is b sine now. So plus 4 times e to the t sine of 2t. And then this is e to the at, where a is -1. So this is minus e to the -t. And there is our answer to this initial value problem using the Laplace transform. All right, here we have our next example. The first thing we're going to do is take the Laplace transform of both sides. So we get the Laplace transform of the second derivative plus 4 times the Laplace transform of the first derivative minus 5 times the Laplace transform of y is equal to t times e to the t. This is on our Laplace transform table. This is t to the 1, e to the 1t. So this is going to be 1 over s minus 1 squared. Where this is the a here, s minus a, and then it's 1 plus 1, and then 1 factorial up there. But that's our Laplace transform of t times e to the t. All right, now let's replace these derivatives with their equivalent. So this is going to be the s squared times the Laplace transform of y minus minus s times the Laplace, or times y of 0, which is 1. So this is just going to be minus s, minus y prime of 0, which is 0. So that's it for this piece. Then we've got plus 4 times s times the Laplace transform of y, minus 1. So distribute that 4, we get minus 4. Minus 5 times the Laplace transform of y is equal to 1 over s minus 1 squared. All right, so now let's factor out the Laplace transforms here and get everything else to the other side. So we get the Laplace transform of y times s squared plus 4s minus 5 is equal to this 1 over s minus 1 squared plus s plus 4. All right, now let's get this combine that into one fraction here. So we're going to need this s plus 4 to be over s minus 1 squared. And to do that, we're going to need to multiply by s minus 1 squared on the top as well. Okay, and then so that is going to be, let's just figure out what that is real quick. So s minus 1 squared is s squared minus 2s plus 1. Multiply that by s plus 4. It's going to be s cubed minus 2s squared plus s plus 4s squared minus 8s plus 4. That's s cubed minus or plus 2s minus 7s plus 4. All right. So this up here is s cubed plus 2s minus 7, 2s squared minus 7s plus 4. All right. Now, so this actually can be factored. This is going to be the Laplace transform of y times s plus 5 times s minus 1 equal to, add all of this together, we get s cubed plus 2s squared minus 7s plus 5 over s minus 1 squared. And then divide by this, we get the Laplace transform of y is equal to s cubed plus 2s squared minus 7s plus 5 over s plus 5 times s minus 1 cubed. All right. So let's put that up here now. The Laplace transform of y is equal to s cubed plus 2s squared minus 7s plus 5 all over s plus 5 times s minus 1 cubed. All right, now we're going to do, we need to split this up using the method of partial fractions. And this is we've got repeating linear factors here. So let's set this s cubed plus 2s squared minus 7s plus 5 over s plus 5 times s minus 1 cubed is going to be equal to some constant a over our first factor, s plus 5, plus some constant b over s minus 1, plus some constant c over s minus 1 squared, plus d over s minus 1 cubed. All right, then let's multiply through by this denominator. We get s cubed plus 2s squared minus 7s plus 5 is equal to a times s minus 1 cubed plus b times s plus 5 times s minus 1 squared plus c times s plus 5 times s minus 1 plus d times s plus 5. All right, now we get to expand all of that. So we get s cubed plus 2s squared minus 7s plus 5 is equal to s minus 1 cubed is going to be s cubed minus 3s squared plus 3s minus 1, and then multiplied by a. So we're going to put an a there, and an a there, and an a there, and an a there. All right, plus b times all of this. So this is going to be s minus s, let's see, s squared minus 2s plus 1 times s plus 5. Going to be s cubed minus 2s squared plus s plus 5s squared minus 10s plus 5. So this is s cubed plus 3s plus 3s squared minus 9s plus 5. Okay, and then multiply by b on all of these. All right, then c is going to be, this is so plus c times s squared plus 4c times s minus 5c. We ran out of space almost. Plus ds plus 5d. There we go. All right, now let's match up our coefficients here on the s cubes. So this is going to be 1 is equal to a plus b. There's no more s cubes on here. The s squareds, we got 2 is equal to negative 3a s squared plus 3b, and then plus c. And then we've got negative 7 equals the s's, which is 3a minus 9b plus 4c plus d. And then the constants, we've got 5 is equal to negative a plus 5d minus 5c plus 5d. Now we just need to solve for a, b, c, and d. And to do that, I'm going to use a matrix. So this is going to be 1, 1, 0, 0, and 1. And then the second one is going to be negative 3 plus 3b plus 1c, 0d is equal to 2. Then we've got 3a minus 9b plus 4c plus 1d is equal to negative 7. And negative 1 plus 5b minus 5c plus 5d is equal to 5. And then if we do some elimination on this, we get, we're going to get that a is equal to 35 over 216. Let me check that, yeah. And b is equal to 181 over 216. C is equal to negative 1 over 35. And d is equal to 1 over 6. So I just plugged that into the calculator, just put this matrix in, and did a reduced row echelon form on it, and found those solutions down there. So let's go back up here, and now let's rewrite this. Our Laplace transform now, the Laplace transform of y is going to be equal to 35 over 216 times 1 over s plus 5. Plus our b, which is 181 over 216 times 1 over s minus 1. plus c, which are so minus 1 over 35 times 1 over s minus 1 squared, and then plus 1 over 6 times 1 over s minus 1 cubed. All right, now we can take the inverse Laplace transform on both sides. This is going to be y is equal to 1 over s plus 5. The inverse Laplace transform of that is just going to be e to the negative 5t. So this is 35 over 216 times e to the negative 5t. This is going to be e to the t, so plus 181 over 216 e to the t. This one here, notice this is t e to the t. We've already done that going this way. So this is going to be minus 1 over 35 times t e to the t. And then on this last one, we've got s minus 1 cubed. So that's s minus 1 to the 2 plus 1. So we need this up here to be 2 factorial. So let's multiply by 2 up top here. And if we do that, we have to divide by 2 as well. So we get this final thing is going to be 1 over 12 times t squared e to the t. And that's it. That's our solution to this initial value problem using the Laplace transform. All right, for this next example, we have a little bit of a twist in that our initial conditions are not defined at 0, they're defined at pi. And that's a problem because remember, when we replace our derivatives, we use that function at 0 and the derivative of that function at 0. So, so we need these initial conditions to be at 0. And the way we're going to do that is by defining a new function. Let's call it y of t. We're going to define that to be w of t plus pi. And so now you can see that y of 0 is going to be the same as w of pi. And then, and if y of t is this, then y prime of t is going to be w prime of t plus pi, and y double prime of t is equal to w double prime of t plus pi. All right. Now we can go through and rewrite this problem with, let's first write everything and replace these t's with t plus pi. So we get w double prime of t plus pi minus 2 w prime t plus pi plus 5 w of t plus pi is equal to negative 8 e to the pi minus t plus pi. And now let's replace these w's of t plus pi with y of t. So we have y double prime of t minus 2 y prime of t plus 5 y of t is equal to negative 8 e to the pi minus pi is going to be 0, so this is just negative t. And then now our initial conditions are y of 0 equals 2 and y prime of 0 equals 12. And now we can solve this just like we solved our previous examples. In fact, this was our first example. So we've already done this on this video about 15 minutes ago. So I'm not going to do it again. I'm just going to tell you that the answer is that y of t is equal to 3e to the t cosine of 2t plus 4e to the t sine of 2t minus e to the negative t. So that's what we got for this problem, but that wasn't the problem we were given. We were given w. So we found y, now we need to find w. And so notice that if y of t is w of t plus pi, then w of t is going to be equal to y of t minus pi. And so let's replace this y of t with y of t minus pi. So w of t is going to be equal to all of this with the t's replaced with t minus pi. So this is going to be 3e to the t minus pi times the cosine of 2t. If we plugged in t minus pi in there, then we're going to get 2t minus the cosine of 2t minus 2 pi. Well, if you subtract 2 pi, you're just back to where you were. You're not changing anything with either cosine or sine. So those are periodic functions with a period of 2. So it's always going to be the same. So this hasn't changed anything by subtracting pi. This is still going to be cosine of 2t. So plus 4e to the t minus pi sine of 2t minus e to the negative t minus pi, so that's e to the pi minus t. And there is our answer for this one. That is the solution to that initial value problem.